Hello everyone, welcome back to Alkaline Hydroxide 784. So if you watched 3.1, good for you. If you haven't, go and watch that first because this is the second part. Of course you don't need to watch that to watch this, but you know, if you wanted to watch everything then you should watch that. Okay, so in the second part of episode 3 we will be covering transformation, including the inverse, how to tackle the inverse and modular stuff, and also the 1 over fx, like the reciprocal, as well as parametric functions. Of course, parametric functions seems like the odd one out here, but I thought I can just follow the order that it was written in the syllabus. Well, okay. Anyways, actually for normal transformation, it is very simple. This is a trick that I learned from one of my maths RA teachers in Sec 4, and basically it is what you call, I don't know, is it for your mother or your grandma, depending on who you are, your ama. And you know, spelled AMMA. And how this works is A represents addition and M represents multiplication, or in other words like scaling, that kind of thing. So for the addition, you start with the x, you know, the x, yeah, you do x addition, then x multiplication, then y multiplication, and y addition. So you just follow this and you're done. Yay, you don't need to memorize anything else, just memorize this and you're good. Okay. But before we continue, let me tell you why this works. Of course you should know why it works, I guess. The reason why you do the x addition before x multiplication is because, okay, let's start with, let's say x, okay, your fx is equal to x, and you decide to add something, you want to make f equals to x plus 1, and okay, sure, you just add x plus 1, like you add 1 to it and you get x plus 1, okay. But let's say you wanted to make it fx equals to 2x plus 1. If you did the 2 first and you made it 2x, then when you add the 1, it would add to both of the x, you know, like 2x plus 2, it will become that, it won't become 2x plus 1. And that's why you should do the multiplication after addition when you're doing, if you want to convert fx equals to x into fx equals to 2x plus 1. So in this case it makes sense. And likewise for the y you do the multiplication before addition. I guess, okay, let's just say let's say y is equal to x again. And you want to make it y equals to 2x plus 1. Yeah, how brilliant. It's actually the same thing here again. It's the exact same thing as doing fx equals to 2. Okay, actually that's really dumb. Okay, maybe let's make it y equals to fx, where fx is equals to x, and you want to make it 2fx plus 1. So if you do the addition first, you will get fx plus 1, and then if you multiply it, it will become 2fx plus 2. Yeah, because you're doing it from the y side, so everything is opposite. If you want to visualize this in a more obvious way, you can do it on the y itself, and then in this scenario you would do the addition and multiplication in the order like you would do with x. So what I mean is, if you want to, instead of saying y equals to 2fx, you can say half of y is equal to fx. See, there's a difference now. That's why when you do things on the y-axis, it seems like the effect that you see is different compared to the things that you do on the x-axis. Like for the reason why they say when you make it 2x, you have to actually do it half, like half in your scaling, or if you put x plus 1, you actually have to move in the negative direction. That's because you're doing it on the x side. If you did the y things on the y side, it would look the same. It would have the same effect in the sense. Yeah. so in this scenario, for the x you would do addition and multiplication first, and y you do multiplication and then addition. If you're doing everything on the so-called x side, the right hand side, if you're going to do your y things on the left hand side, then you can follow addition and multiplication, that same order for both. Yeah, that is the summary of my transformation thing. Okay, so TLDR, just follow that AMMA and you're good. Good. Okay. So the next thing that you do is, so the next thing I'm gonna talk about is how to, make fx into, for example, fx inverse or f inverse or f of x modulus or something like that, those things. Okay, the first one, I think you already know how to do it. I would have talked a bit about it in the previous episode. For f inverse x, you can just draw the x equals to y and then just reflect it across that. Simple. No need to think hard about that. And the most important thing is to make sure your scales are equal so that your graph is more aesthetically pleasing and also easier to draw, honestly. And the next one is f of x modulus, right, where the modulus is inside the brackets. And in this case, your x is always positive. So what you do is, you can have a negative y, but if, like, let's say your graph is what, x, let's say x cubed, your graph is fx equals to x cubed. If you're doing f of x modulus, then your x cubed graph will look like a weirdo. Like the part in the positive x-axis is the only thing that is reflected over to the other side, and that's what you get. So, or maybe, for example, if you have something that looks like a hyperbola, although that probably may not be a function, but if you have something that looks like that vertical hyperbola, if you did the same thing to it, it will be like reflecting only the right part over to the left side, but it will still look the same. So I don't know what I'm saying. Anyways, so that's how the f of x modulus works. You only reflect values on the positive x axis. The y can be negative, but you take the right hand side of it and you just flip it over, and you get your f of x modulus. But on the other hand, if you get modulus of fx, I think this one is more easy for everyone to do, which is just make sure all the negative things are pushed upwards to the positive. And yeah, that's about it. And you don't have anything in the negative for whole thing fx as modulus. Okay, so the next one is the reciprocal 1 over fx, and for that, that's probably the one with the most things to take note of. And if you had practice with it, good for you, because it helps a lot if you had prior practice with this. If you do not have prior practice with this, then I have nothing to say. You just need to practice quite a bit to get the hang of it. And once you get the hang of it, you don't need to practice. I'm just kidding, you still should practice. Just every now and then, just make sure you know what you're doing. And for that, the reason, if you want to understand why it works, I will explain it as I tell the individual stuff. Okay, so the first part is, that is 1 over fx. So, like, for example, if your x is going towards, okay, your fx is going towards infinity, what will you do? 1 over infinity will go towards 0, so makes sense, right? Whatever is going out of the graph now goes towards the axis without intersecting the axis. And if fx is going to 0 or intersects at 0, in this case you cannot make it intersect at 0 because 1 over 0 is not defined. So but it will go towards infinity instead. And in that scenario, you have to draw an asymptote, the vertical asymptote, and make it go towards infinity. Or if it didn't intersect the if it didn't intersect the line axis, you can just make it go towards infinity. Yeah. those are the first two things to take note of. And the second thing to take note of is the existing asymptotes there, where it is going towards infinity, but there's an asymptote. So in this case, you would make it intersect the axis, but I think in A level you're allowed to just let it intersect, but the true right thing to do is to draw a circle in the place where it intersects, because that is not necessarily an actual point belonging to the function, because in the original function it doesn't have that point. So in this case it shouldn't have the point, and the point is undefined, so you'd have like an open circle there, which would represent, when you write your range, you have your curly brackets instead of the square brackets. Yeah, that's what it represents. So it's like, for example, if your asymptote was x equals to 1, when you're drawing this, that circle means that it's not there for x equals to 1, but it's there for everything until before and after that. Okay, so the next thing is the horizontal asymptotes, and for that, if you had something that was originally tending towards 0, then it will go to infinity, so that's different. But for other horizontal asymptotes like 1, 2, 4, whatever, any number, even negative ones, then you would have to do the reciprocal of the asymptote, because that makes sense, right? Like originally it was going towards 1, but okay, not 1, let's 1 is 2, is like, 1 over 1 is just 1. It's not a useful example. If it goes towards 2, now it would be going towards 1 over 2. Doesn't that make sense? That makes a lot of sense, right? And even if you consider all the points before that or after that, whatever, those, like for example, maybe before it was at nearing 2, it is at 4, and in the reciprocal to just be 1 over 4, which is lower than 2. So yeah, it's the same thing, it makes sense. So you just need to, that's why that works, it just works. So if you have your horizontal asymptotes, you just draw an asymptote that's inverse of that, and same goes for minimum maximum points. So I don't think I need to re-say the same explanation for that. And that's why they work. So those are things you need to take note of. And was there anything else? I don't think there's anything else to really take note of. But if you want some general ideas of how the shapes work, you can just look at the very simple graphs. Like for example, 1 over x is what x looks like in the reciprocal form. 1 over x squared, 1 over x cubed. You can look at all of them and then see what they look like. And then you can just apply the same logic to your 1 over fx. For example, if it looks like a curved smiley face, then when you make it inverse, it looks a bit like what 1 over x squared does in the sense, yeah. And then the final thing to take note of is when you're drawing your reciprocal graph, make sure that all the positive stuff is still in the positive area, and all the negative stuff is still in the negative, because 1 over fx doesn't make a positive into a negative, it just remains the same. Yeah. And yeah, that's about it for those things. And the final thing we need to cover today is parametric functions. And well, I do not know why they exist, but they exist, that's the point. So the idea of a parametric function is that they use a parameter. In this case, they like to use t. I do not know why they like to use t. They like to use t, or they like to use theta, which is that thing that they like to use for angles. Okay, so in this case you have a parameter theta, and both x and y are dependent on theta. And okay, actually t is easier to say than theta. So the t has a range usually, and if they usually like to use this for trigger functions, so the t will have like a range from 0 to 2 pi or something like that, and then your x and y are dependent on it. And what they usually like to do is they ask you to convert it into a y dependent on x kind of thing, or they ask you to draw the graph. Of course, everyone likes to take out the GC, change it to parametric mode, and then just plot it in. But If you don't like using your GC, once again, there are ways to figure out how to draw it, because if you can convert it into a y equals to something something x, then you can draw it without a GC. But if you are not able to do that, you can think about it. You can try to see how the x and the y change as the t changes. Like for example, if you see that x is goes towards 1 and then goes towards 0, and then y is going towards, wait, what am I trying to say? I don't know. So I said, if you see x is going towards like high or something, and then y going towards 1 and then 0 or something, then you would be having a trigo equation there. But if both of them are trigo equations, like, maybe x is sine t and y is cosine t, what is your final function? It's a circle. Yeah. Why? Because sine square t plus cosine square t is equals to 1. Great. So in case you actually see that, just remember it's a circle. There's nothing crazy about that. But you must see where t is defined, because it may not be a full circle. Yeah. So in that sense. So if you look at how they are plotted generally, then you might get an idea of the shape. You can also use differentiation to see the shape of your graph by doing individual differentiation, dx or dt and dy over dt, and then from there, if you divide dy over dt by dx over dt, you will get dy over dx. The reason why this works is because that's just how the way differentiating, because that's just how those terms work. That whole, it's like the chain differentiation. That's why it works, because of that. Yeah. And from there you can find out many things. Yeah. You can see where the minimum and maximum points are, and if there are any asymptotes. For the asymptotes, you can see whether x or y goes to infinity at any point of time. If they don't, then there probably aren't any vertical asymptotes. Or you can see whether they tend towards 0 or something like that. You can use those tricks to figure out what the graph looks like, and you can draw it without having to worry about anything. And just in case your GC told you something wrongly, this can be like your second checking point, I guess. Like you can use your GC to check your work and your work to check the GC. Yeah. Yeah, I think that's about it. I have nothing else to say. And the next topic will be what's the next topic? The next topic is equations and inequalities. Okay, cool. And with that, if you enjoyed the video, please press the like button and subscribe. And with that, I would like to say thank you and bye.